Hello everyone, and thank you very much for the introduction. And I'm really sorry that I couldn't participate in the meeting today live, but I hope I can give you some useful information also via this pre-recorded talk. Again, my name is Andrea, and on behalf of my colleague Elke Kersten, also from DLR, we are very happy to give you a small excursion on history of planetary cartography and especially on the map layout. Both of us are working in the field of cartography and GIS for planetary science since more than 10 years now and could support and participate in different mapping initiatives and individual map creation. But this should be enough about us, and let's start with our short excursion. Let's start with some definitions. Talking about cartography, it can be said that it is one of the most important communication channels between users of spatial information. It covers a wide area of different information and knowledge levels, and consequently it ranges from a technical and engineering focus to a scientific distillation process. Regarding maps, I like to hint to this definition, which was given by the International Cartographic Association in 1995. They said that a map is a symbolized image of geographical reality representing selected features or characteristics resulting from the creative effort of its author's execution of choices and is designed for use when spatial relationships are of primary relevance. And why I bring this up here is because of the part where the creative efforts of its author's execution of choices is mentioned. This is not only important for the abstraction, the visualization and the description of complex phenomena, situation and processes on a smaller scale, then also for the layout of every individual map. And this applies to all known real-world objects located here on Earth and the maps, or on any other objects and maps of our solar system. So what you can expect in the next 14 minutes is given here. In the first part, I like to start with a very short and very abstracted view on the history of planetary cartography, followed by different types of map we have in this discipline. The next part will show you the map elements that every map should contain for effective communication of the spatial information, and all this with a focus on geological mapping. And in the last part, I will present you a specific map layout of a map series or a map atlas, which was created in the last years at DLR and with our participation within the Dawn mission. But let's start, and let's start nearly 3,600 years ago with one of the oldest visualization of our sky, the sky disk of Nebra. And this disk shows the world's oldest concrete representation of an astronomical phenomena we know so far. And so I think it is a great starting point of the space and planetary exploration phase. In the following hundreds and hundreds of years, a lot of further ideas, theories, visualizations came up how the humanity explained the sky, the space, and the planetary bodies they could observe with their own eyes during that time. The ideas are mainly driven by different scientific, philosophical, and regio-cultural foci over the whole time. Then, a great and huge step. Around 3,000 years later, Leonardo da Vinci started thinking about our nearest neighbor, the moon. And so he visualized the moon in 1500 with a great amount of imagination. And this sketch is given here, and it is as much as impressive as no one had ever been to the moon before, and the most people didn't even know that Earth orbited the sun. And so with this sketch from Da Vinci and further ones like the moon sketch by William Gilbert from 1600, the so-called pre-photographic phase of space exploration was opened. Moving on, the invention of the telescope in 1609 and 1610 by Hans Lillihe and further by Galileo Galilei gives the great push also and especially for the space exploration. This event marked a milestone in planetary exploration because observatorial evidence could be started replacing reasoning-based natural philosophy. Additional, the telescopic view of the moon was not only scientifically exciting, but it was also appealing for the general public. Drawings of the moon done by Galilei on the right and Harriot in the middle are the first hand-drawing figures of our neighbor, and they served the same purpose as photographs today, and so illustrate something which can be detected via our eyes, but so they are not real maps. However, they are also some map-like figures because the illustrator had to use some mapping principles of the generalization and made decisions of classifying the surface features and using icon representations as part of the drawings, for example, for repeated features such as craters. Beside the moon maps in 1659, also the first sketch of the Mars was drawn by the Dutch astronomer Christian Huygens, and he used a telescope of his own design, which has a magnification of 15 times, and this was much stronger than previous telescopes. Via the invention of the telescope, all the human beings of the following 115 years have had the possibility to discover much more planetary bodies, as you can see here in this short list down under on the slide. During the upcoming century, many improvements were introduced, and so the extraterrestrial mapping became a scientific discipline, and we could understand this as the starting point from the cartographic area in planetary sciences. And here the map design was determined by the artistic talent of the observing astronomer or his financial status to hire a good engravers, while the level of details was determined by using the specific telescope. A milestone in planetary mapping is the map of Tobias Mayer in 1749, which is showing here in the upper right corner. And Mayer first used some control points which were measured via the telescope and which became a standard procedure afterwards. And he established the lunar coordinate system with the equator and also the prime meridian. A further impressive map of moon was given a little later by Beer and Mädler and called the Mappa Selenographia. This map not only includes exact measurements in their cartographic visualizations, then also a detailed description of lunar formations like the Mare, the mountains, and especially the crater Tycho. However, besides taking a look to our nearest neighbor, parallel observations of other planetary objects started during that area. And for example, you can see here the impressive and famous map done by Schiaparelli in 1888, which shows the straight line work and straight line linear structures on Martian surface. But also different other maps from Mercury were created in the same manner, which you can see here on the slide. Then, at the beginning of the 20th century, the next exploration began, and the reason for that was the former invention of the photography and the usage of this technology also for the space exploration. So the first images of Mars could be taken at the Lowell Observatory in Arizona, and many images followed in the next years. And due to all this improvements of discovery, the International Astronomical Union, the EAU, presented the first standard Mars map with all surface objects known so far in 1957. The next step meant the most substantial change in terms of the level of details and the number of observing possibilities of the planetary bodies of our solar system. And here I'm talking about the sensor and spacecraft phase. And this started with the Russian and US driven missions to Moon around the 60s and moved on with the formation of the space agencies a little later. And beside this, also working groups like the systematic survey of near-Earth objects and potential hazards, asteroids, were also formed in the next years. So we can say until then the era of planetary mission phase had begun, and the whole chronology of the lunar and planetary missions could be seen here. In parallel to the exploration, also the reproduction techniques for cartographic products change over the time. And here I'd like to give you an impression how cartographers work in the early times of the map production. This lasted for a long time until finally different developments came up at the beginning or at the middle of the 20th century. And one essential one was the so-called airbrush techniques, where drawings of the topographic structures on a map could be impressively improved, and what you can see here within this small image. Certainly, the invention of the computer represented a significant change also in our scientific discipline, like anywhere else. And here the development of a specific software also contributed to an increase in the field of planetary mapping and planetary cartography topics. I'm talking about the development of modern geographical information systems. And I'm absolutely sure and think, especially after that week, you have an impression for which task and which different application GIS software and GIS technologies could be used in our field of planetary mapping. But besides desktop GIS applications, also further attractive technologies for map making and map representing came up in the last years. And I talk about the virtual reality tools. And what you can see here is a VR interface currently developed at DLR. But this is an ongoing development process, and a lot of open issues still exist, but I'm very sure the solutions are not far from now, and we have some other developments, similar developments in the planetary science from other parts. With this, I'd like to stop the very short historical overview and excursion, but if you like to know more about that topic, you can find further information within these references. But now let's move on to the next part, the different map types we have in planetary sciences. First of all, we have the image or the photo maps, and here the different planetary surfaces are visualized via the combined satellite data to a homogeneous mosaic, and mainly this is combined with the labels of the surface features. And here you can see some nice image maps of Mars, of the asteroid Vesta, of the Saturn satellites, and also of the Venus. The next map type are topographic maps, and these maps do not only show the surface as also detectable via our eyes or via the photographs and the mosaics. The maps are also combined with situation, terrain, and a number of other phenomena which are needed for the topographic orientation. This topographic information could be visualized via a color-coded value, for example, of the underlying digital terrain model, which you can see here by this Martian or by this lunar map in the left down corner, or it could be visualized by so-called hill shading, which is a technique to show the topographic shape of, for example, hills or mountains using a shading on a map. And this is just to indicate the relative slopes of mountains, ridges, not the absolute height. And this hill shading is a prominent layer on a map of the Mars moons on the right-hand side, in the middle top, and on the multilingual map showing on the right upper corner on the slide. The last type of map, what I like to categorize here, are the thematic maps. And sure, here some of you could ask why the topography is not also a thematic map or a theme. And this is an absolutely correct question, which also hasn't answered in the terrestrial cartography discussion so far. And if I try to give you the difference between the two types, I would say the topography is something which is estimated via direct measurements, for example, and all other topics and themes need some human interpretation, some additional information and calculation, or both. But as I said, the distinction isn't absolutely clear. Anyhow, if I talk about thematic maps in planetary science, we do at least add one additional layer on the base map, which means, for example, images or topography, and describe predominant phenomena or events which are associated with the surface directly. A very small insight of the great value of maps we have in planetary science are shown here and give some examples of the Martian and the Mercury surface. Beside the great treasures of analog maps of former times, and apart from systematically created map sheets, nowadays the maps and map-like figures are mainly available as figures within scientific publications, as digital map files, as supplemental material in the paper publication, or sometimes within individual created WMS and WFS services. And as I think that exactly these kind of map representation are interesting for you, because then you could show and communicate your scientific results within a map, I would like to show you in the following slides what you need for an effective map layout. And so move on to the next part, to the map elements for an effective communication of space research results within a map product. Therefore, I like to take a closer look to one specific map product, and this map was created within the systematic mapping program funding by NASA and coordinated by the USGS, which produced a lot of high quality and so-called standardized maps regarding the procedure of production and the revision process. The map I have chosen therefore is the quadrangle of the investigation map number 666 with the name Cassini, that shows the geology of the lunar surface at the upper mid latitude of in a scale of 1 to 1 million. This map sheet is one part of the Geological Atlas of Moon published by the USGS, which is available if you follow the link what you see on the slide. How the map sheet is integrated in the surrounding area and the border map sheets you can see here within this figure I created within a recent publication. But the whole image and the whole map, in my personal opinion, a very nice map sheet is given here, and you can have a quick look on that. But now let's disseminate it into the different parts in the different map elements which are needed for the map creation. First, we like to concentrate onto the map area itself, but this is much more than just the map area. In cartographic speaking, this contains the map field, the graticule and map border, which strongly depends on the map projection, and as additional graphical element, the nomenclature. The map field itself is mainly dominated by the mapped features and in geological maps by the colorful geological areas and the line work for linear features. But as our focus is the map layout and the topic of a great balanced cartographic design within the mapping area of all the visualized features is a very specific and comprehensive topic, I will not talk about this here. The only thing I want to mention here is first, choose the position of the map field depending on the other map elements which have to take place on the map sheet. And second, also maps have a reading direction like text, for example, from left to right. And the second point means to first position the map mainly on the left-hand side of the map sheet, and then the descriptive elements, and then order the descriptive elements and the other and further elements around that, mainly on the right-hand side of the map sheet. If we take a closer look to the map field, we can see two further elements, the map border and the graticule. The map border could be understood as border between map field and anything else on the map and could be just visualized by a simple line. Whereas the graticule describes the spherographical coordination system showing as line for latitude and longitude on the map. And here we can see a 2 decimal degree distance of the map. The graticule is the essential element to place the map field in a larger context and to orientate the map reader also in the whole map field and to orient with all the different objects you can find on a map. As mentioned, the graticule and map border depends on the choice of of the map projection. The map projection. The map projection is the systematic representation of a round planetary body on a flat surface. And each map projection has specific properties that make it useful for specific purposes and areas on the sphere. And here you have to choose between more or less distortions in length, in area, and also in angle. And what you can see here is in my point of view, nice overview of the most used map projection within the USGS, for example. But let's move on. The last element I like to show in the context of the map field is optional in map making, but mandatory for geological maps. I talk about the nomenclature, and this text work on the map describes the individual names within the map field and was improved and what improves the orientation of the individual localization of the map features, the areas, and also the phenomena. Coming back to the entire map sheet, we go on to the next element, and which is one of the most prominent, especially for geological maps, the legend. The map legend is essential in order to understand all the areas, the lines, the points, colors, patterns, and letters visualized within the map area. Within geological maps, it describes much more. It also explains the correlation and composition, the stratigraphy between the different geological units. And so it is absolutely essential within a geological map layout. The next part I like to show, or the next element, is the scale. And sure, every map has a scale already because it is a conversion factor between reality and the map sheet. But how the scale is indicated on a map could be done differently, either by simply by a written number or as a graphical scale, which is shown here. And the importance of scale in general was also mentioned during the mapping week and during different presentations you could see during the week. And the reason for that is just if first the mapper knows the scale of the base data during the mapping process, he or she could interpret it, the base data exactly and correct. But this is also a consequence for the final map sheet, because just if the map reader know the map scale already, and also he or she can read and interpret it, the map content correctly and bring the elements potentially in a context of other maps. And so the scale is a very important element of the map creation. The next element is as simple as important, and I talk about the map title. And if you take a closer look to our example here, the title is the geological map of the Cassini quadrangle of the Moon. And the first impression is that the title is complete and meaningful. If I would argue from the traditional cartographic point of view, I learned, so to say, rule that the title of a map should contain the spatial context, the topic or the theme of the map, and in best case, the scale. As the scale is very close written to the title in our map example, I would like to stick to it. It is a well-chosen and meaningful title. However, in order to also include some information like the map is one part of a collection, which is not unimportant in my point of view, could be given in a subtitle, for example. But now, as you heard enough for the title, and you know the title is important also for a map design. And let's move on to the next element. The next element is an optional sitemap. In our example, this is an index map of the Earth side hemisphere of the Moon and the lunar orbiter photographic coverage of the Cassini quadrangle. The benefit of a sitemap is that you can either indicate some background or overview information like you have here in this example, which indicates to the quadrangle scheme of the map where the map is based on, but you can also include some detailed view of a specific area, for example, which has an important interest for you and your scientific research within the map at a higher scale. And this fact could solve some scale problems and scale issues within your mapping process and the choice of the mapping scale over the whole mapping area. And so you could have some different types of scale within one map sheet and could guarantee a consistent mapping scale within these two map sheets and within these two mapping fields, the detailed map and the general map field. Having this in mind, move on to the nearly last element, which is specific and thus essential for the geological mapping. I talk about the profile, a geological profile. The profile that describes the composition and layering of the different geological map units via a cross-section, as this is elemental, especially to understand the stratigraphy and the stratigraphic statement you like to communicate in your map. This should actually be part of a geological map if you produced a single map sheet and if the profile is not included within the combined scientific publication, for example. Now we are almost done through all the map elements and only one is missing. And the last element seems to be optional, but are also important to comprehend and understand the map story in general. The elements are the background information and additional descriptive information. In our example, the background information describes the elevation in the map, for example, the used datum and different control points within the map, and also explain the nomenclature and the type of nomenclature on the map. The descriptive information tells the geological history as a summary, and here also scientific interpretation results and also essential references to other maps and publications could be included here. And with this last element, I like to close this section on the map elements and move over to the map layout. But if you're interested in the topic of cartographic aesthetics, the efficiency and the science in planetary cartography, I like to hint to the recent paper which discussed exactly this components on the previous example, the Cassini quadrangle on the Moon, within the publication, which is linked here. With this, we came to the last part of our talk, the exemplary map layout. As I said, I will demonstrate this by two different map series which were created in the last years at the DLR and in our participation within the Dawn mission. And what you can see here is a global high altitude mosaic, so-called HAMO mosaic, of the dwarf planet series. After creating this mosaic, one first task was to divide the surface in different tiles. One important reason for that is to minimize the distortions on the different surface regions. There are several schema available which are chosen depending on the size of the planetary body and the resolution of the data. And the tiling schema which was used by for the HAMO mosaic is comparable to a previous schema for the Mercury and divided the surface in 15 tiles. And so 15 so-called map quadrangles are available for the different areas. The 5 equatorial quadrangles, we have 4 in the mid-northern and 4 in the mid-southern latitude, and 1 for each polar region. What you can see here are the detailed overview of the quadrangles with their border coordinates, the numbers, and the quadrangle names. And the quadrangle names were chosen by the dominant crater of every quadrangle area. Okay, so far so good. What is next? The next step was to create a map atlas or a map series out of these quadrangle mosaics with all the information we had so far about the surface in order to use exactly this information as base maps for further investigations of series, for example, to do some geological interpretation. This important step was done by my colleague Elke Kersten, and what you can see here is an exemplary template of the map layout via the Dantu quadrangle in the northern mid-latitude. The template was created not in GIS software because you have some limitations within the GIS, then in the graphical software afterwards, and it contains all necessary map elements we presented in the previous slides. Taking a closer look to the template, I like to show you some more details. Beside the graticule information you have in the map on the map frame or in the map border, the 3 templates for the 3 site maps in that case, the graphical scale on the right-hand side, you could also see some very fine line work within the mapping area. And these line works are the contour lines of the topography or of the mapping area. And this is a great element, especially within the image maps, to give an impression about the absolute heights of the surface topography. And this contour lines based on the underlying digital terrain model, which is also a high quality and derived product within the Dawn mission. Within a further and closer look, I like to hint to the chosen naming abbreviations of the map within the general notes. Then not only the tiling schema or the nomenclature followed a predefined recommendation, then also the map number. And the map number here is AACH 750K 43.5/135 COMT 2017. And what does this naming abbreviation means? It means that it is a map of the asteroid Vesta in HAMO resolution. The scale is 1 to 750,000. The center points in degrees consisting of latitude and east longitude from 43.5 to 135. It is a controlled orthophoto mosaic with nomenclature and contour lines, and the publication year is 2017. Subsequently, after finalizing the map template, this was combined with the previous created mosaic data of the quadrangle and finally gives this comprehensive map sheet and the map layout. As you already heard before, this map sheet is one part of the whole HAMO, so-called High Altitude Mapping Orbiter Atlas created at DLR. And an overview of all the map sheets is given here, and all the data are available if you are following the link down on the left-hand side in the left-hand corner. So far, so good. As I said, this is not only the only map layout we created within the Dawn mission. We had also another task. And this task was to create a further map layout for the geological mapping project within the Dawn team. And here 15 individual scientists each take one quadrangle and interpreted this area from the geological and geomorphological perspective. In comparison to the map sheets within the HAMO Atlas, these map sheets were created in order to publish the individual maps within the planned scientific publications, which was created for every mapping and quadrangle area individually. But in order to find also for this map series a comparable map layout, we also started here with the definition of a map layout template. One template for each different regional map type. The 4 types you can see here and are divided in the northern and southern mid-latitudes, the polar regions, and around the equator. The 4 types you can see here are visually comparable to the templates of the HAMO Atlas, and the reason for that is that the map reader should recognize something like a corporate identity within the whole map layout. If we take again a closer look to the template of Dantu, we find the following elements here on this map sheet. We have the legend, which describes the individual units, the lines and the points of the maps. In comparison to the map example I showed you some slides before within the Cassini map sheet, the detailed description is missing here, and the reason for that is that the whole detailed description of all the geological information is given in the paper which is related to the map and not on the map themselves. And beside this, we do have detailed information of the scale and the used cartographic projection. And this is individual for every map sheet and are essential information to understand the dimensions showing in the map area and to understand the distortions which are still given within every map due to the choice of the cartographic projection. And if we combine this template with the geological mapping project data of the specific quadrangle and the underlying HAMO mosaic as background, we could create this map sheet for all the individual quadrangle data and with all the individual and needed components. Again, comparable to the slide for the HAMO maps, you could now see here all the map sheets which are created within the geological map project and are published as supplemental material within the special issue of Icarus, what you can see here in the left down corner. Beside this, we also create some further map sheets on a global scale, one in Mercator and the stereo projections for the polar regions, and equal area Mollweide projection in the right-hand corner. Having these last maps in mind, I'm at the end of my talk for today, and I'd like to sum up with some hopefully useful information for you and your further and next map layout. The map elements for efficient communications are the map title, the scale, the map field, the map frame, subtitles, the legend, the sitemaps, and also the source and the information. Consider about the minimum scale and the level of generalization within every mapping process and map project. In order to minimize distortions in relation to the purpose of the map, be sure about the chosen map projection and think about your audience, your final format, the medium and the color. As a final hint, I like to refer to a paragraph which is given in Robinson's Elements of Cartography. And he said that balance in cartographic or in graphic design is the positioning of visual components so that their relationship appears logical. Nothing should seem out of place. Layout is the process of arriving at proper balance. In a well-balanced design, nothing is too light or too dark, too long or too short, too small or too long in the wrong place, or too close to the edge. After this small excursion in planetary cartography and map layout, I like to close the talk for today. Just one last thing I have in mind. If you are interested in this topic of planetary cartography in general, I like to invite every one of you to a commission named Planetary Cartography within the International Cartographic Association. Together with Trent Hare from the USGS, I have the pleasure to chair this commission. So please feel free to visit the website and get in touch with us. It is just for fun and networking and without obligations. If you have any questions related to the presentations today, please feel free to contact me via this email address, which is shown on this last slide. And with this, I'd like to thank you for your attention and all the interest in the whole mapping week and the planetary map layout session. And now I'd like to give the mic to Alessandro Frigieri, who will give you a great insight how you can create the map layout within QGIS. Thank you and bye-bye.